Okay, guys, welcome to the next session. In the previous session, we just discussed about multisim combination logic circuits, and we developed a basic combination logic circuit by using independent digital constant and single pole double throw switches. Now, the next is the use of multisim logic converter to do all of these things. So all of these things we have practiced manually before, but now we will take help of this software, how to extract a truth table from the combination logic circuit, extracting expressions from the truth table, okay, the Boolean expression by just looking at the truth table or the combination logic circuit, we made Boolean expressions. So we will do it by using multisim. Simplifying complex expressions and logic circuits. As I told you before in our previous discussions last week, that when you develop a combination logic circuit, sometimes it gets very complex because you are working based on logic, but you can simplify that logical expression and the logical circuit into a very sometimes very small circuit, which will result into less energy use and a quicker response, so which is very important in these days in electronic gadgets. So you need electronic gadgets with the low power consumption and fast response and less heating up. So all of that is possible by simplifying complex expressions and logic circuits. So developing truth table from the expression, okay, vice versa, and logic circuit, developing logic circuits from the expressions. So all of these options we will discover in multisim logic converter. Remember we did this example in our previous lectures where when I showed you this combination logic circuit, as you can see on the screen, which is using few NOT gates, AND gates, and one OR gate. This is the truth table for that for this combination logic circuit. And then I showed you that this logic circuit can be simplified by this one in the bottom right. Okay, this is using less number of gates, less connections, less power consumption, and quicker response. So the truth table of both the logic circuits would be the same. Actually, truth table is the behavior which we want. We want when the input combination is like this, the output should be like this. The G is the output. So that's how we want. So this circuit can provide this truth table, but this simplified circuit can also behave in the same way. So why to use extra gates and extra energy to do that? So that's why it is very important to simplify your logic circuits. We will see this in our multisim. I actually made this circuit before. Let me see which one is that. Yeah, I think this is the one. Yeah. So guys, this circuit here is the same as you saw on the presentation. This is the one. Okay, 3 NOT gates, 2 AND gates, 1 XOR. So you can see there are 3 NOT gates, 2 AND gates, and 1 XOR. There is no XOR. There is no OR gate. Sorry, there is no OR gate with the 3 inputs. So I just simply use 2 OR gates to do the addition of these 2 inputs and then do the addition with the third one. Okay, so this is the same combination logic circuit which you saw on the presentation. I just showed you in the previous session how to construct a combination logic circuit by using multisim tools from here. Now I will move on to the next point. Once the logic circuit is made, then you can use a instrument from the right side panel called logic converter. I'm hovering my mouse onto the logic converter written there. So this is the logic converter. The same are placed on top here, on the top left corner. Okay, you can see that there is a input is missing. Like I did not use a SPD to use independent digital constant. I did not use any one of that because I'm using this logic converter that is giving inputs. Okay, so logic converter, you can see there are many pins. All of these pins are in, except the last one. It can handle, of course, one output. So this one is last one. Last pin is always for the output. So the output is connected from here. Okay, and because this combination logic circuit has three inputs, so the three inputs are being connected from these 3 points. You can see that. All right, guys, are you with me so far?
Oh yes, here. Yes, teacher. You were about logic, the logic converter, and how it has
Okay.
a lot of inputs that's shown, and
Yeah,
the last one is the output, right?
yeah. The last
This
one is
is
the output. Rest of all,
this is same as what is it called? Same as the gate that we use in this a board. Remember, like in the in the up top lab, same as a board. It does have
in
like a
previous course.
16 legs, seems like that.
Yeah, yeah,
Uh,
not exactly that I see,
uh,
but this is different one. This is a special tool in this multisim. I will
oh,
show
okay.
you how to use it, then you can understand its functionality. So if I double click on this, it will show me all of this information. Okay, so because it is already connected in this logic circuit, so it is telling me how many inputs are there: A, B, C. These are highlighted, three inputs. All the combinations, input combinations are already there, and this is the truth table. This is the output actually. This last column on the right. If you look at this, first four are ones, followed by two zeros, and then 1 0. If you look at this, it's same. First fours are ones, followed by 2 0, and then 1 and 0. So the truth table is same. So you can see this on the right side. There is conversions written here. Conversions. So these are all different conversions possible here. The first one is if you click this first option, that means from logic circuit to truth table. Okay, when I made this circuit first time and I connected my logic converter here, okay, then I press this button, then it will show me this truth table. So it means you develop any logic circuit of your choice on the multisim. You connected a logic converter here as shown on the screen. Okay, connect the inputs and connect the output. It will automatically, it will apply all the combinations on the circuit and it will generate a truth table for you within seconds. Okay, so the truth table will come up here like this. Right, from here, from the truth table, you can develop the logic expression. Can you see when I click this second option? This is the logic expression, which is the logic converter is showing. So this is the logic expression of this logic circuit. All right. So you can do it manually as well, but the logic converter is doing it very quickly for you. Okay. So you can see it says A A inverse dot B inverse dot C inverse plus then all of this. So you can see there are inversions here in the form of NOT gates, and there are addition functions are going on with all of this, and there are multiplication functions going on with because of these AND gates. So all of this is shown here with one click. Now, how to simplify this? There are so many gates here, and the logic expression seems very complex, but as you do algebra and you simplify the equations. In the same way, in the Boolean algebra, this is called Boolean algebra, which deals with the digital or binary numbers. It has also similar to the normal algebra. You can simplify the expressions to make the combination logic circuit more simple. If I want to do that by using this converter, I will just click the third option, which is to give me a simple SIMP is written, give me a simple expression. So here you go. This is a simple expression you can see here. This was the complex one and the simple one is this. Okay. Now if I want to make a circuit based on this simple logic expression, then I need to click this button here. Okay, when I click this, it's processing to generate a circuit, and you can see this circuit is the equivalent circuit. When I click it, it will come up here. It's the same as I already pasted here before. Okay, so I will just delete this. So you can see there are two logic circuits side by side. This was the original one, and with a complex Boolean expression, but we simplified this into a more simpler logic circuit with a simple Boolean expression with the help of this logic converter. Okay, now look at this. It shows you two NOT gates, one AND gate and one OR gate. Let's compare it with our presentation example. You can see this in the bottom right corner. It's the same circuit, two NOT gates and one AND gate followed by one OR gate for addition. So it gave you the same solution here. So it means our example, which we did last time, uh, with the help of MULTISIM, we are able to verify that, and we can, with the help of this useful tool, which is called logic converter, you can do all of these conversions from logic circuit to truth table, from truth table to expression, and you can make a simplified expression. You can simplify your circuit, and also if you have expression, and you can develop this truth table. Okay, and you can create a based on this expression which is written in the bar. You from this expression you can generate the circuit as I just did, this equivalent circuit. And there's one more option to develop a logic circuit only by using NAND gates. If I click this, then it will create a logic circuit in which only the NAND gates will be used, no other gate. So here you can see three inputs A, B, and C. There are three NAND gates. There is no other gate used in this. No NOT gate, no AND gate, not OR gate. So how it is helpful? Because you are using only one type of gate. Okay, and it is giving you the same exact same behavior as this complex circuit was giving, or this equivalent circuit was giving. It will also give you the same truth table. So these are all of the options which you can try by using logic converter. Okay, if I make a new design here, let's say, and if I bring up my logic converter here and I double click it, okay, and I can from here I can develop a truth table. Now I will show you by just using this logic converter. Let's say I am using a 3 input logic converter. Okay, so it has already developed all the input combinations. Now I can decide what is in my mind. I want a truth table whose first input should be 0, second should be 1. Okay, when you click it, it will change the value. Third 0, fourth again 1, fifth 0, sixth again 1, seventh 0, and eighth again 1. Okay, you can make any truth table here, any truth table of your choice. There is one more option to bring up x. X means you are okay with any type of output here. Okay, if you put x, it could be 0 or it could be 1, anything. It means this combination is not important for you, so you can put x there, but I am putting 1 here, for example. Okay, now what I will do, based on this truth table, I want to, for example, if I want to make an expression, truth table to expression, if I click this, it will give me expression here. You can see this Boolean expression, which looks quite complicated. If I want a simpler one, I will just click this. And the simpler one, you will be amazed to see that it is only showing you one letter, which is C. So we will see that how does that happen. Okay, let's first, from this logic expression, which is there in the bar, if I develop a logic circuit, how will it look like? So I'm clicking this option here, from expression to logic circuit. So this is how it will look like. Quite a complex one, you can see. It has a lot of gates, lot of connections, lot of things. Okay, but the equivalent one, you will be amazed to see that if I click the simple expression C and I click the equivalent logic circuit for that, it will look like just like this, that the input C is coming at the output. Whatever is at C, it is coming at the output. It means that, so no need to do all of this complex circuit, okay, which is total, you can say, waste of so many gates and waste of energy. So the whole of this thing is just giving you C as it is on the output. So this is very useful feature while designing the things, and you can practice by yourself. I mean, if you want any, you can develop, you can start from the truth table, or you can start from the expression. Okay, let's make a new one. Bring up a logic converter. If you can, you want, you can start from a expression. Let's say A dot B inverse plus C dot A inverse, for example, and anything you can type in. Right. So I just typed any expression of my choice. Let's put one more inverse. Let's say, okay. So by using this expression, if I want to develop a logic circuit, so this option, from expression to circuit, I will select, and it will give me it will give me a logic circuit like that. So I hope it is very easy for you guys. You will like this tool when you use it. So this is the expression. If I want to make it simple, let's see if it can simplify this or not. There are no inputs defined in the truth. Okay, we need to put the inputs. Okay, you need to somehow you need to generate this truth table first. So after creating the truth table, then you can simplify the expressions. So based on the truth table, which is the exact behavior of the logic circuit, then it will see what simplest combination is possible and what simplest expression you can get from there. So guys, this was all about the logic converter, which I used in the example which was in your teaching course. So I showed you how to develop a combinational logic circuit, how to use the logic converter, and by using that, how to simplify the combination logic circuit into a more simpler version. Any question, guys, on this?
Teacher, my question is, I'm trying to understand this, the left one, I mean the right one. Like this is a diagram. What is it? I don't know why my mind is getting stuck when I see this.
Okay, see, the thing is,
Yeah.
this combination logic circuit on the left is
Yes.
giving you a behavior in the
Yeah.
form of a truth table. Let
Okay.
me show that truth table here. This truth
0, 1.
table.
Okay.
Yeah, it shows that with this input combination, these input combination are fixed. Okay, there are three inputs, and there will
Yes.
be eight possible input combinations. They will
Mm-hmm.
be fixed. They will never change. So based on that, for each input combination, you get a certain output. Okay,
Yes.
so you are a designer, and you want that when my input A is 1, when my input B is 0, when my input C is 0, my output should be 0. Okay, and when my input A is 1, when my input B is 1, when my input C is 0, my output should be 1,
Mm-hmm.
which is here G. Okay,
Yes.
so you want like that, you want a circuit which should behave this way. This truth table is actually the, you can say, the behavior of the logic circuit. Okay, and you come up with this design. Okay, your key point is this behavior, this truth table. You don't want any complex circuit behind it. So the same truth table can be uh, shown by this simple
Mm-hmm.
logic circuit. So the simple logic circuit can do the same job as this complex one can do. So the same
But
thing is being
how
shown here.
how how it can do this, but with less components? I mean, less gates. Sorry.
Yeah, that's gates. Yeah, it can do that because see, basically the gates are just doing the switching. Sometimes they are switching the states two times or three times, which is not necessary. For example, excuse me, if you are inverting something here,
Mm-hmm.
for example, if you are using not gate two times, I'm giving you example. So how will be it useful? One NOT gate will change the state, other NOT gate will bring it back to the original state. So using two NOT gates, you can simply exclude them. You can take it out, but still your uh, truth table or your logic circuit will not be affected. Are you getting my point? It's think about a thing in mathematics as well. For example, you say 100 over 50. The answer is 2. 4 over
Yeah.
2, 4 over 2. Again, the answer is 2.
Yes.
Okay. So the the thing which is mattering, it is actually the behavior, the truth table that you want uh, this behavior to be shown by the circuit. You can show this behavior by a complex logic circuit or by a simple logic circuit. We will go for the simple logic circuit because it will be with less components, with less power consumption. It will have more faster response because remember, each gate will take some time to change its state. Although that time will be in nanoseconds, but imagine if there is a very complex combination logic circuit with in which there are hundreds of gates or thousands of gates are involved, then what will happen? All those nanoseconds accumulated together will end up as a delay. And these days, in this modern era, you need gadgets with the minimum delay. You need fast response. You need more battery life of your gadgets. Okay, so power consumption should be less. So that all makes it very important that whatever output you desire in the form of truthable, you want to make it with minimum components with minimum power consumption. So that's what you can get from this logic converter. Okay, so both the circuits are doing the same job, but with the one on the right with less components and less power. Okay, guys,
All
any
right.
any other question, guys? Okay, the recording will be available for you to review anytime. So thank you for listening. I will stop the recording now.